I want you to name each of these triangles as detailed as possible using both angles and sides. We'll talk about it in just a minute. Okay, so the first one is what? It's scalene and obtuse. This one. Isosceles and acute. How about this one? Isosceles obtuse would be correct. This one here. It's a right scalene or scalene right, either way. This one is an isosceles right triangle, or right isosceles, either way. And finally, scalene acute. The one I didn't put up there, what's that one? Equilateral. Do we have to say acute for that one? No, if it's equilateral, it's implied it's acute. Because if I go back up here, let's say the 3 hashes, the number of hashes also is an indicator of length. Which has to be the largest angle, A, B, or C? A. Why? It is opposite the longest side. So down here, what do each of those angles have to be? 60. Because the sides are the same, the angles they're across from have to be the same. So they're all the same, and a triangle adds up to 60. Or to 180. Yep, it's always named by the largest angle. This one is acute because the largest angle is still acute. Because you can't possibly have 2 obtuse angles in a triangle. Because obtuse is greater than 90. 2 of them greater than 90 would be greater than 180. So let's get to stuff that are more than 3 sides. Let's talk about polynomials. So obviously, the 3 sides is called a triangle. We've been talking about those for a while. 4 sides is called, that's a special type. Those are both special types. Quadrilateral. Quad meaning 4, lateral meaning side. Now there are several special types of quadrilaterals that we'll come back to in a couple minutes. 5 sides? Pentagon, yes. The agon comes from polygons. It's a 5-sided polygon. 6, hexagon. 7, there you go, septagon. 8, octagon. 9, heptagon. 10 is decagon. Deca coming from, decade for 10, or deci, 10. Of course, the 7 and 9 don't happen very often. Usually you have even-sided things. The pentagon does happen often enough that the 5 sides is useful. I'm not going to force you to memorize those or anything like that. But let's go back to that one we said has a lot of different A lot of different ones. That's the quadrilateral. The quadrilateral itself is any shape with 4 sides. Now, the one I actually drew there ended up being a special type of quadrilateral because those 2 sides are parallel. A quadrilateral that has one set of parallel sides is called a trapezoid. A quadrilateral that has 2 sets of parallel sides is a parallelogram. Now, because of what we learned yesterday about parallel lines, these 2 lines are parallel and these 2 lines are parallel. It should tell us something. First of all, this angle and this angle have to be the same because this angle will be the same, this angle will be the same, this angle will be the same. There's like 8 of them there that are all the same, right? This angle and this angle have to be the same because there's another, the other 8 are going to be equal to that one. What's the relationship between this one and this one? Remember, parallel lines are either the same or not complementary, but supplementary. Add up to 180. So in a parallelogram, angles that are in opposite corners are equal. Angles that are next to each other are supplementary. When we get into trig, that supplementary thing is going to be very important. Now, that's just a parallelogram is just a generic figure with both pairs of opposite sides equal. Or both pairs of opposite sides parallel, I should say. If those opposite sides are parallel and equal, it's a special type of parallelogram called a rhombus. A rhombus is a parallelogram. So if I gave you that figure, if you called it a parallelogram, that would also be true. Now, another special type of parallelogram, opposite sides are still parallel, but now all 4 angles are equal. In other words, all 4 angles are 90 degrees. It's called a rectangle. A rectangle is a parallelogram. Something that's even more special because it's a parallelogram with all 4 sides equal, a rectangle with all 4 sides equal, or a rhombus with all angles equal. It's a quadrilateral with all 4 sides equal and all 4 right angles. It's called a square. There are other special types of quadrilaterals. These are the ones that occur often enough for us to name them. So if I were to draw a shape, name it for me. Pentagon. Has 5 sides. It doesn't have to be your typical, pentagon like that. That would be obvious that's a pentagon. But the pentagon just has to have 5 sides. Now we're used to seeing one like this where all 5 sides are equal. That would be referred to as a regular pentagon. So all the sides are equal, and in a regular polygon, all the angles are equal as well. How about this one? Okay, it is a rectangle. What else is it? It is also a parallelogram. What else is it? Quadrilateral. Very good. Everybody see where all those come from? How about this one? It's a square. What else? It's a rectangle. What else is it? Parallelogram. Also, it's a rhombus. Also, quadrilateral. Yeah, it fits a lot of different categories, doesn't it? A square fits every special category. How about this one? It is a trapezoid and quadrilateral. Now, just like we had something called an isosceles triangle, you can have an isosceles trapezoid. It just means those two sloped sides are the same. Yeah, these two angles would have to be the same, and those two angles would have to be the same as well. If you think about it, if I cut these off, you know, these two heights got to be the same because those are parallel lines, right? So this is going to be the same. This is a right angle. If these sides are the same, I have two sides that are equal in a right angle. Well, a squared plus b squared equals c squared tells us those two have to be the same. I've got all three sides the same and one angle the same. And technically, if you have all three sides the same, that's all you need to prove that two triangles are equal. Let's actually take a look at that quick. What do I need to prove that two triangles are equal? If I have all three sides, so let's say I've got that length, and that length. Is it possible to build a different triangle with those same three lengths? Well, let's think about it. I'm going to start out with a line here. I'm going to take this length here. I'm going to mark it out on that line, right? So there's that length. I'm going to take this length here, and I'm just going to come out and I'm going to make an arc at that length. This is kind of like doing construction with a compass. So I've made that length. From here to that arc is that length. So I'm going to make this length. So I'm going to start from here. I'm going to make an arc that long. They cross in only one spot there, don't they? There is exactly one triangle that can be constructed with those three lengths. I cannot construct any different triangles. Any triangle I construct with those three side lengths is going to be equal, or a mirror image of it. So it's still that's in geometry that's still considered to be what we call congruent. If it's a mirror image, it has the same sides and same angles. It's still congruent. So having all three sides the same makes two triangles congruent, or the exact same triangle. What about if we have a side, an angle in between them, and another side? Well, what does that mean? Well, that means I have this type of situation. I have this side, I have this angle in between them, and that side. Well, if I have a side, an angle, and a side, that's going to give me this shape, right? Is there any way to connect these two ends that's different from any other way? No. So that's going to give us two triangles that have to be the same. Or congruent, yes. How about two angles and a side? Well, So let's say I've got those two angles, and either the side between them or the side, any of the sides, to be honest. Well, if I know that two of the sides of these triangles are the same, or two of the angles, I should say, are the same. So I know this angle and that angle are the same as those. What do I know about the third one? It has to be the same because a triangle adds up to 180 degrees. If two of them are the same, the third one has to be. So basically, if I have two angles, I have all three angles. If I know all three angles are the same, that tells me that they're at least similar, doesn't it? If one side is the same length, well, then not only are they similar, they are congruent. One of the definitions of congruent is similar triangles with a aspect ratio of 1 to 1. So the sides are the same length. They're similar, they have the same angles, and the sides are the same length. So any combination, whether I have two angles and a side that's not between them, or if I have two angles and a side that is between them, either one has to give us equal triangles. How about this one? Two sides and the angle that's not between them. Now up here, it was two sides and the angle that was between them. Down here, it's two sides and the angle that's not between them. I have this side, I have this side, and I have an angle here. So I got that same side, right? I'm going to do the same angle. That side's the same, but those are different triangles, aren't they? In this one, this was an acute angle. Here, it's an obtuse angle. And I could have folded that side in here or out here. So if I have two sides and an angle that's not between them, it is possible to make two different triangles. This is going to become very important when we start talking about solving triangles. Law of sines, law of cosines in particular. That's going to be very important. Now, of course, I was careful to arrange that as SSA, but if you spelled that backwards, of course, yeah, which is no good for anybody, right? So then, let's look a little bit more at our quadrilaterals. Let's look at the angle sum. Actually, let's look at the angle sum of any polygon. We used the parallel lines the other day to prove that triangles have to add up to 180 degrees. Well, let's look at a little different way of doing this. So I'm walking down this side of a triangle, right? Heading in that direction, and I turn here so that now I'm going in this direction. I walk down that side of the triangle, and I turn here. So now I'm going in this direction. So I walk down there and I turn here. Now I'm going back in the same direction I started, aren't I? So I'm going to call this angle A, B, and C. What do I know about the sum of angles A, B, and C? 360 degrees. It's a full turn, right? If this here is angle D, what do I know about A and D? A plus D is 180 degrees. If I call this angle E, what do I know about B and E? 180. It's a straight line here, right? If I call this F, what do I know about C and F? 180. So if I add those three together, that is 540, right? So what I have here, all six of those angles add up to 540. If I take out A, B, and C, how much have I removed? 360 degrees. D plus E plus F has to add up to 180. What I did there was I had three corners. Let N be the number of vertices. Now that's also, by the way, If it has three corners, it also has three sides, right? So n can also equal the number of sides. Each vertex, each vertice was 180 degrees, wasn't it? So I had 180 times n. Gave me those total angles of all six of those. In any figure, it would be the total angles. But what did I subtract from that? Yeah, the outside angles, which are 360. The angle sum of any figure is 180 times the number of angles minus 360. Now, your textbook adjusts this a little bit. It does something called factoring, which is just reversing multiplication. It takes out that 180 and writes it like this. Now, if you're looking at that, wondering why is that the same? Well, what's 180 times n? 180n. What's 180 times negative 2? Negative 360. Writing it this way is just a little bit simpler. So if I have an 8-sided figure, that's just going to be 180 times 6, right? N minus 2. So that's 1080 is the angle sum. Does that make sense? It's 180 times the number of sides minus 2. 2 less the number of sides. So let's take a look here. Obviously not a regular polygon. Find that angle for me. I'll give you a minute. How many sides does this have? N equals 6. So the angle sum is 180 times 4. 720 degrees. Remember, 2 less. Yep. N minus 2. So 720 total degrees. Well, let's add up what's there. So yes, we're going to add up 149, 152, 81, 128, 99. Oops, come on now. Appears to be 609. So subtract 609 degrees, there's 111 degrees left. So that must be 111 degrees. Not so bad. Oh, good. Let's look at some special cases of triangles. Let's say I have this big triangle here. This side here is, let's call it 9 inches. Let's call this side here 12 inches and 15 inches. I'm going to draw another triangle. I'm going to tell you two things. This side and this side are equal. This is 10 inches long. If I want to find those lengths, what can I say about those triangles? Well, obviously this angle here is equal to itself, isn't it? How about this angle and this one? Because those lines are parallel, those two angles are equal. How about this one and this one? Again, because those two lines are parallel, those two angles have to be equal. So we have similar triangles here, don't we? So that means we've got that ratio of 15 to 10 has to equal, if I call this one x, 9 to x. Cross, multiply, and divide. X should be 6. We've got that same ratio, 15 to 10 equals 12. If I call this one y, 12 to y. Cross multiply, 10 times 12 is 120. 15 is 8. That's 8 inches. So those two triangles, if I have two triangles that share two sides and the third side is parallel, they're similar. What if I have this triangle here and let's call this side 12 inches, 18 inches, and 21 inches. I tell you that obviously it shares this side, but I'm going to tell you that this is parallel to that, and this is parallel to that. I didn't do a great job of drawing them parallel, but you get the picture, right? So I'm going to draw this out and extend this out, right? This shape right here is going to be what? Parallelogram. This side's parallel to that side, this side's parallel to that side, which means this angle and this angle are the same. Of course, that makes that angle the same. They're vertical angles, aren't they? Well, if these are parallel, this angle and this angle are the same. These are parallel, this angle and this one are the same. So once again, we have similar figures. Now, I'm not going to bother finding sides here, but you know how to go about doing that. Here's the one that I think is just kind of cool. This is a right triangle. Let's say this is 18 inches, 24 inches, and 30 inches. You can verify that, by the way, with a squared plus b squared equals c squared. It should work. If I draw what's called an altitude goes from one vertex of the triangle to the opposite side at a right angle. So my altitude is going to come from that right angle to the opposite side, making a right angle down here. You know, a distance is always measured at right angles to a line. So the altitude is just the distance from a vertex to the opposite side. Well, if I look at this here, this angle, of course, is equal to itself, isn't it? This right angle and this right angle are equal, right? Well, then, because the triangles add up, all angles in the triangle add up to 180, this angle here and this angle here have to be equal. So what that means is this little triangle formed here is similar to the big triangle formed. So in a right triangle like this, where we have all three sides, we can always find the length of this altitude. If I call this length here x and this length y. Now this is where it gets kind of tricky. I'm going to go with little triangle and big triangle here. What is the hypotenuse of the little triangle? That's the 18. What's the hypotenuse of the big triangle? 30. Right? That's across from the right angle. What is the smallest leg of the little triangle? X. What's the smallest leg of the big triangle? 18. Right? Big triangle's on the outside. As I said, this is kind of confusing because we're looking at the same drawing, but we're taking two different triangles out of it. The 18 is the small leg of the big triangle, but it's the hypotenuse of the little triangle. So now to find that missing side x, it's 18 times 18 divided by 30, which is 108. 10.8. You divide by 3, not 30. X is 10.8 inches. By the way, that means this length must be what? 19.2. How did I get that? Subtracted from the 30. Very good. Now I could do a squared plus b squared equals c squared, but let's be sneaky. You got a little triangle and a big triangle. 18 is still the hypotenuse of the little triangle. 30 is still the hypotenuse of the big triangle. Y is which side of the little triangle? Y is the longer leg, right? So the longer leg of the big triangle is the 24. So now it would be 18 times 24 divided by 30. So at 14.4. Does that sound right? So y is 14.4. So we can find those missing lengths of those little triangles. We can find all the sides of them. Now there are other shapes here, other things on triangles that we can look at. What we found, I don't want this to look like a right angle here. Let's do this. So in altitude, I'm going to color code these. So we're going to go from vertex A to side BC. So vertex A, of course, is just that. Side BC is this. Right? In altitude, remember the distance from that vertex to the other side, it's measured at a right angle. So it looked like that. Well, there's also something called a median from vertex A to side BC again. A median cuts that opposite side into two equal pieces. So the median would look like that. Those two pieces would be equal. Yeah, that should be in the center. Yeah. Call both of those X. They're the same length. It cuts BC in half. Well, then there's also something called an angle bisector. An angle bisector would look something like this. It cuts angle A in half. So those two angles would be the same. Notice the altitude, the median, and the angle bisector are not the same lines here because this is a scalene triangle. But if I have an isosceles triangle, and I do the altitude from A to side BC. Well, obviously that angle and this angle are the same, aren't they? because this was isosceles, this angle and this angle had to be the same, didn't they? Well, if two of those angles are the same, third one here has to be the same. Well, those two angles are the same, which makes that line, I'm going to label it AD, makes it an angle bisector because it cuts that angle in half. If all three angles are the same, obviously this length and this length are the same, and of course this length is equal to itself. That makes the triangles equivalent. Remember, all we need is, if we have all three angles, all we need is one side. We actually have two of them. Makes them equivalent, or congruent. So that means those two pieces are equal, which makes it a median. So if this is a isosceles triangle, if we know that it's a median, we know it's also an angle bisector and altitude. If we know it's an altitude, we know it's also an angle bisector and a median, and so on. If it's one of the three, it is all three. What do you think? Oh, come on now. Let's go ahead and give you your homework. In the packet, this should be, I think, the last page of homework in your packet. Page 295, 1 through 24. Of course, I'll let you work on the odds.